Okay, welcome back to our 10th lecture and the tutorial in Python. Today we'll implement our first neural network in PyTorch and Python, and we'll just continue where we left off in lecture 10 to implement a feed-forward network to solve the XOR problem. So just to remind ourselves of the XOR problem, this is a binary problem in which we have two variables. Those can be 0 or 1. So all the combinations are 0, 0, 0, 1, 1, 0, 1, 1. And we learn that problem, or the problem is first that if these values are the same, then it is a 0. And if they're different, it's a 1. Or if one of them is 1, it's a 1. If both of them are 1, it's a 0. And both of them are 0, it's a 0. And this is the table. We know that from the lecture. And the first thing we want to do is we want to import this into PyTorch. So the first thing you do after you install PyTorch is you want to import it. So import torch is the command to import PyTorch. And then there's some shortcuts. So a lot of people do this, import torch.nn as nn, and nn gives us the neural network components. So for example, nn.Module gives us the neural network modules that we'll implement later. And there's also nn.functional, and there's nn.embedding, for example. There's many different things in this scope. So it's good to have this imported as nn. Otherwise, we have to write torch.nn.module and all that stuff. So in this case, we're just shortcutting that. And the first concept we want to know more about is a tensor. And a tensor is very similar to a NumPy array. So if you have a equals np.array, and you write some numbers here in the list, 1, 2, 3, this is very similar to a torch.tensor of the same attributes. So what is the difference then? Why don't we just use np.array? And in fact, a lot of times what you will do is you will just move from torch.tensor back to np.array. The thing with torch.tensor is that first you have the capacity to move everything that is in a torch tensor to GPU. So if I have torch.tensor, I can also call to, and then I can say what device I want to have. So it could be, for example, it could be instead of CPU, could also be CUDA. And CUDA means this is actually transferred to a NVIDIA GPU if you have one and you have the drivers. I don't have this on the MacBook here, but if you're on a server, you can call to CUDA and it will run this on GPU instead of CPU. And that helps you to parallelize things later. So tensors are multi-dimensional arrays of values. And in this case, we just need a two-dimensional array, and that is the training data. So we call XS is a torch tensor of 2 dimensions. So here's the first dimension, and then each of them rows here has another dimension. And the Y is our training, our labels, and that's also a torch to tensor, but it's one-dimensional. So the problem with one-dimensionality later is that if we don't reshape it here, we can do that. So we call this cell, and then we can see the shape of XS is 4 by 2. That's exactly what we want. So it's this array, and it is on device CPU, as we've seen. If I call now XS to CUDA, which we can do, it will throw an error because my machine doesn't have CUDA. But if you have CUDA, then you can transfer this to GPU. The type is float32. We put the dot here, which indicates it's a floating point. Otherwise, we could also use int. Since gradients and the neural networks are computing floats anyway later, it's a good idea to do this in float. And now Y shape is just 4. So there's the problem I was talking about. So now this is just an array, just a one-dimensional tensor. What we want to do is we want to reshape it so that it has another dimension. So later we can broadcast them, because 2 tensors of different dimension cannot be broadcasted. So this has 4 times 2, and this has now 4 times 1. So this missing dimension, we just added it there. So we can do operations between them. And so that's the array we are seeing now. And now what we can do already is we can build our neural network. So we have two inputs, right? We have two inputs. Let's go back here. Two inputs per training sample. So those are here, the rows. And now we want to build one layer of weights for these two inputs. So we call nn.Linear. And what nn.Linear will do is it will create a weight matrix and a bias for each input neuron, that's the first argument, and each output neuron, that's the second argument. So in this case, we want to have two input neurons and one output neuron. And we can then see what are the parameters by taking this component and calling the parameters function, which returns the model parameters. And here you can see what I meant before. The data is a torch tensor, but we can also bring it back to NumPy by just calling NumPy. So let's run that, and we can see that in the beginning, these weights are automatically initialized by PyTorch. So the weights, the perceptron weights, are 0.373, 0.591, and the bias is 0.2707. So those things are now initialized. We're just missing one thing from before. We don't want it to be linear. We want it to be nonlinear. So that's where we use the ReLU function. Again, we can import torch nn functional as f, so we save some time. We don't have to write torch.nn.functional.ReLU, which would also work. And you can have all these input arguments, but we can just write f.ReLU, and it will also give us this. So the ReLU function of 1 should be 1, of 0 should be 0, and of -1 should be 0. So if you look here, if we insert -1, it is 0. If we insert 0, it's 0. And if it's 1, it's here also 1. So that should output the following. And now we can construct our actual network. So before, what we did is we would define the individual linear layers, or the linear layer, it's just one here, in the code. But PyTorch gives us a way to organize these into modules. So if I have a larger component that does multiple things, for example, a neural network, that's something I would want as a nn.Module. So here we inherit a class XOR from nn.Module, and nn.Module just asks us to implement a function called forward. And in the initialization, it asks us to please identify what are the learnable parameters. So here again, something that we're doing is, actually here is the sigmoid. Oh, that's great. We can change that. So what we're doing here is we create a linear layer of 2 by 2, and that's the hidden layer. Okay, so those are the input neurons, and now we have 2 hidden neurons. That's great. And then we apply sigma, or we define a sigmoid function, self.sigmoid. This should actually be lowercase. We define the sigmoid function, and then we apply to that neuron another linear layer, 2 times 1. So from the hidden layer to the output layer. And we just define here these things. We don't actually do them yet. So that was just one step too far. So we define them here. Those are the learnable weights. We have here 4 learnable weights and 2 biases, and we have here 2 learnable weights and 1 bias. Okay, and then here, now what we do is we take the input of the forward point function, and we shouldn't use the keyword here, so we just call it imp. We apply the first linear layer to the input, and x will give us the output of that. So that's the hidden output state. And then we apply the sigmoid function to that, which we then call sig. And finally, to the y hat, we apply the linear layer 2, and that should be 1 output. Okay, so this is now with a sigmoid function. We don't want to do it with a sigmoid, but let's try it with a sigmoid, and then we do it with the ReLU. And that's also great practice to see if you can change that easily. Okay, so this will give us the module, but yeah, that doesn't do anything because it's just a class. So first we want to initialize the network. We can do that in a separate cell. Okay, so let's create a cell here. I don't want it to be marked down. Can delete that. So let's create the network. And this will give us, this XOR network will give us a neural network. Then you can see here in features 2, out features 2, there's a bias. Then we have a sigmoid function, and we have in features 2, out features 1. It's exactly what we wanted. The next thing we want to do is we want to measure how good the network is. So we define the mean squared error loss. That is already implemented in PyTorch, so we don't have to worry. Just call nn.MSE loss, and this will give us an instance that we can call later to measure the loss. So this will not give us any loss, of course, but later we can use MSE loss, and we can call it with the parameters, so y and y hat, and this will give us the loss of these two. And also we create an optimizer. So here, this is the actual gradient descent optimizer. Here we use Atom, but in the lecture we just looked at SGD, which is stochastic gradient descent or gradient descent. And we pass it the network parameters. So those are all the trainable parameters. Let's go here, dot parameters. Okay. And that's a generator, so we can get all of the elements, element for element in these net parameters. I just do this list comprehension. This will iterate over the generator and return a list, so we can actually see it. Did you forget a comma? L for L in? Yes, I forgot a keyword. And now we have the actual parameters, and you can see these parameters are tensors again. Okay, so those are the parameters of our model. This is the first weight matrix, 2 by 2. This is the first bias, 2 by 1. This is the second weight matrix, 2 by 1. And this is the second bias, 1. So it's exactly what we wanted. Okay, so we can use SGD, and we define a learning rate 0.03. You can also go 0.01. And then we can create, we can actually measure this once. So let's get y hat by forwarding the model. So we call network.forward with the training data, and this will give us the predictions. So the predictions are 0.2, 0.3, 0.1, 0.2. And if we compare that all the way back to the predictions that we needed, which is 0, 1, 1, 0, this doesn't look right yet. And why is that? Because we basically randomly initialized the network. So there has no learning taking place. So if we measure the loss, it should be rather high. And if we do that, the mean squared error loss gives us 0.34. Ideally, the loss should be 0. So if the loss is close to 0, that means it has already been learning good. Okay. And if the loss is higher, then this means the predictions are not good. Okay, so now that we created the loss, we can call the backward function, which will compute all the gradients for us. So all the manual gradient computation we've done in the lecture can be done by one function call, loss.backward, and loss.backward will give us the gradients. So if we now take the first linear layer, the weights, and then grad, which is gradient, as we've seen in the lecture, this is stored locally in this object. We see that the gradients are this. And you can already see that the gradients are quite low, which might be also because of the sigmoid function. We can change it later and see. And there's also gradients of the bias. So now we can call the optimizer step function, and that will enable us to do a step, which means we take the weight and we subtract the learning rate time the weight, the gradient, and then we will reduce the loss function. So we can see the weights before updating and the bias before updating. That's here. And then here you can see what it looks like after updating. And some of these have not changed significantly. So you can see here in the last digits the change, and here in the bias there's also just the last digits that changed. But if we do this multiple times, then we will have a bigger update. If we put the learning rate to 0.8, for example, or 0.5, which is really high, and we do that again, you will see much more significant change. So now 0.6417 to 0.6394. That's a pretty drastic change in the weights. So let's go back maybe 0.05. And we've demonstrated now how that works. And something that is a little bit unique, I would say, for PyTorch that other frameworks do differently is the optimizer zero gradient method. So you see PyTorch accumulates the gradients per default. So if you compute a gradient and then compute another gradient, it will just accumulate the gradient of each value. It will not reset them. And that's important in a training loop where you want to reset the gradients. You have to call this function. Otherwise, you will accumulate the gradient over training all the time. And at some point, you have really high gradients and exploding gradients or too low gradients because they're reducing all the time. So if you call that method, all of the gradients get set back to 0. Okay, so now we have all of the components for putting them into the recipe, putting them in the training loop that we actually need to optimize this problem. Again, here is the Atom optimizer. Let's go to stochastic gradient descent. So we initialize the network. We define the number of epochs, in this case, 1,000. You can also reduce that to 100. Usually, it depends on the problem, but usually you have something like in the low single digits to, in the high single digits to low double digits, but it really depends on the problem. We define the loss function. We define the optimizer. We did that before. We create a list to store all the losses, so later we can plot them. We save an integer or a number to store the current loss, and we want to define when we plot every epoch. This should be named plot every epoch. And that's when we actually plot something or we actually print something. Let's keep it at 1,000 so the script doesn't die. So now we have a very simple for loop actually. So for epoch in range epochs, so this will be a counter from 0 to 1,000, or basically a 999. And this will be one epoch. We compute the y hat, which is the forward pass of the network, using the entire training data. And if you have larger training data, here would be something like for batch in, and then you have something like a sample function from access. And then everything here would be shifted towards there. And instead of calling directly access, you would call the batch. Okay, that's something very common. And sample function can be something that the access, oops, that was not by, nope. Okay, access doesn't have to be loaded in memory at all. So sample function could take a reference to a data directory. Okay, and the batch could be loaded without access to have been ever existing. Okay, so imagine you have millions of documents or millions of images. You cannot store them in memory usually. So you have some sort of sample function from a data directory, from a table, from a network that you can use to load the batches. In this case, we have the training data in memory, and each batch or each iteration is the entire training set. Okay, so we don't have that problem. So if we forward the entire training set, we get all of the predictions that we've seen before for each of the classes, which are for each of the cases, which are 4. We calculate the loss between our actual true value and the y hat. Okay. And then we backward the loss. We compute all the gradients. We compute the new weights. We remove the gradients so that they don't accumulate from here. Otherwise, the gradients would be something like, I don't know, x.grad is here 1, and then x plus 1 dot grad, is equal to 2, and then this goes on. And this is something that we don't want, because in each step, we just want to compute the current gradients of the current step. Okay, and then we append the current loss to the full loss, so we have the entire loss, and we plot every epoch only if the epoch modulo the number of epochs we are is 0. So it would plot at 0, 50, 100, 150, and so on. To all the losses, we append the current loss divided by the amount of steps it takes to compute the loss, and then we send that back to 0. And also, if the epoch, this can also be, if the epoch divided by 500 is 0, so every 500th epoch, we want to plot that this epoch has ended. We can do that every, let's say, 100 epochs. So if we do that, plot every is not defined. That's great. So plot every epoch. Somewhere here it's wrong. Yeah, plot every epoch. We changed that variable name. So now this goes really fast. If you have a large network, it takes much longer, but we completed the 1,000 epochs. It just doesn't plot on the last one anymore. We can change that by saying probably something like +1, then also the last one. Epoch. If epoch modulo 100 is 0, so if epoch +1 modulo 100, then we also get the 999th. Okay, and then we're done. And now we can visualize how the loss behaved. And this loss actually gets stuck at 0.25. So there's always one thing getting wrong in the network. So let's see, that's also exciting. I didn't see that before. So those are the weights and the biases that we have. And if we now forward an example like 1, 1, so 1, 1 should lead to 0, this will return 1. So that's actually wrong. So the network didn't learn right. And 1, 0 should be actually 1. And this returns 1. And 0, 1 should also return 1. And 1, 0, 0 should return 0. So all of them are right. But this one here, so effectively, this neural network just learned the OR function. That's interesting. So it learned the OR function, not the XOR. And that might have to do with how we define here the, let's see, we changed some things, I remember. So if we use Adam, which is a version on top of gradient descent, stochastic gradient descent, it might move the network out of the local minimum. Let's see if that changes something already. Okay, let's show the loss. And the loss gets to 0, so it overcomes that local minimum. It also gets to this problem here, it seems, but then it goes out of that minimum. And the parameters changed. And also interesting, those are not the parameters that we found in the lecture, like the 4 1s and then 0 minus 1 for the bias, because there's probably infinite solutions to neural networks and their problems. So you'll always find probably a little bit different weights. Here again, let's not use the keyword input, but instead imp. And now we get 0, 1, 1, 0. Great. So now the problem has been learned. So actually here we can observe that training networks does not always lead to the global optimum. And learning the OR problem is already the best thing that could be achieved using SGD in that case, because the local minimum could not be overcome, it seems. So this is actually a practical example in which this didn't work. If you want to take a look, Adam is just an iteration on top of SGD, which helps with some things like regularization of gradients and overcoming local minima. There are some parameters like beta and beta 2, also beta 1 and beta 2 that you can choose. There are many different variables that you have to take care of. We call them usually hyperparameters, and the way you choose hyperparameters determines also the success of your model. So even though we didn't learn the XOR problem with SGD, we learned the OR problem, which is close enough in terms of the loss because we couldn't find anything better than that. Also, one thing to note is that we here take the full training data, which we usually don't do. We do that batch approach. So that's also something why we might not find the best minimum with SGD, because it has to take into account all the different variables. And if 3 of them are already quite good, it's reluctant to go into a direction in which the fourth would be optimized, because 3 of them are already right. So yeah, thank you very much for listening. The tutorial, the notebooks are online, so you can also check them out yourselves and play around with the different parameters and weights. You can construct a larger network or different optimizers, different losses. And we'll see you in the next lecture 11, where we will implement transformers and BERT from scratch. So there's more complex models to explore. And then see you in the next one.